Just gonna check out.
I feel. All right, it's 3 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Doing good. Yeah, hopefully everyone's enjoying the start of the World Cup. I'm always reminded of the story whenever the World Cup comes around. Um, I haven't had a chance yet, but I am interested, of course, watching the World Cup. So I'm always reminded of the story. When I was in grad school, I think this was like 2014. I was taking a class from the Spanish professor, and if you know any bit of World Cup lore, Spain lost very bad in 2014. I think it was it Germany or was it Netherlands? I don't remember. But anyway, so it happened around this time, which is around finals time for the quarter system. And I was walking down the hall. I was just trying to go to the bathroom, and then I run into the Spanish professor, and I knew he was in a bad mood because Spain had just lost by like 6 goals. So I was trying to not make eye contact with him, but then he called out to me. He's like, "Did you see the games?" I was like, "No," and he's like, "Spain lost by 6." I'm like, "Oh, yeah, that's pretty bad." He's like, "You think that's bad? I'm gonna go grade your finals right now."
Oh,
And then all my friends like, "Oh, why'd you piss him off? Why'd you piss him off? And I was gonna grade our finals." Like I was just trying to go to the bathroom. I was trying to piss him off. But yeah, everything was okay. I think all my friends passed, and I passed, and so. But yeah, kind of a funny story. Yeah. Okay. All right. So luckily for you guys, I'm not a particular fan of any one country in the World Cup. I'm just looking to see good soccer, good football. So if a particular team loses by 6 or more, then it's not going to affect how I grade your guys' exams. Okay. So with that said, we are starting something new today. So today we're starting our unit on potential flow. We are starting and finishing it today, just because that's just how the summer session works. So this is kind of a big shift in terms of what we're doing compared to all the control volume analysis that we've been doing. So all the topics for today will not be on the midterm exam next week. So midterm exam next week is just going to focus on control volume analysis. I was considering maybe adding this topic to the midterm exam, but I think just because I won't be able to give you guys a homework on this. The homework on potential flow will be due next Sunday. We'll save this topic for the final exam. So midterm exam next Thursday with just control volumes. Okay. Speaking of the midterm next week, I did post the study guide, and so if you look on the Canvas site for week 3, part 3, there is a study guide for midterm 2. So make sure you guys check it out. Midterm is going to be 1 week from today, next Thursday. So that is June 18th. And so it'll be in class, just like the first exam, for the first 80 minutes. And so please be here. Same rules as the first exam. You can bring your writing utensil, bring a calculator. You can bring a cheat sheet, 1 8.5 by 11 sheet, front and back. You can write whatever you want on it. And then we'll take the exam next week. Okay. Homework 3, members due this Sunday. Homework 3 is basically going to be your practice for midterm 2, because that's homework 3 is basically all your control volume problems. I'm going to post solutions for homework 3 probably on Tuesday. Just because I want to give it a day, just in case people want to turn in late. Just so you have that. And homework 4 will be posted sometime tomorrow as well. Okay, so I'm going to post homework 4 early, but just keep in mind that homework 4 will not be on the exam. I just want to post it just so that for those of you who are ahead, you can start working on it. Okay. All right, so I think that's all my announcements. And then, right after their second midterm next week, then we'll have the final exam the week after that. So we'll talk about the final exam next week. But we'll kind of take it just one step at a time. Another announcement. So I did post the solutions for midterm 1 as well. So if you go under the same page for this week, week 3, part 3 on the Canvas site, you'll see that there's a PDF there for the midterm 1 solutions. Okay. I'll have the solution. There's solutions there for the short answer problems as well as the problem solving questions. Okay. Keep in mind that remember there are 2 versions of the midterm, and so I do have the solutions for both versions on there. Just make sure you find the right one for your exam. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay, so today, so the broader topic for today, in terms of what I want to get to, is a topic called potential flow, which is a very big area of fluid mechanics. But we do have to kind of introduce, we do have to kind of work ourselves up to it. So before we get to that, let's talk about what I define as differential analysis. Okay. All right. So at this point, we're all done with control volume analysis, and control volume analysis is interesting because control volumes are a great way to analyze, entire fluid systems or entire fluid, devices. Okay? So if you've noticed, one thing from control volume analysis, we're always looking at usually an entire component, like an engine, or maybe an entire, vehicle or an entire fish sometimes, right? And so if you want to look at kind of a system as a whole, then control volume analysis it's very much, input, output, overall effects type of analysis, right? So I think, some people would define this as kind of like a high level type of analysis. And obviously, that has its place in engineering systems and engineering design, right? So if you're working as a systems engineer, you high level analysis is part of what you're going to do because you want to see how different components are going to act with each other. So you're looking at overall design and overall kind of inputs and outputs for a system. Okay. But that's not the only way for us to study fluid mechanics because, when you do such high level analysis, when you look at kind of components as a whole, you kind of, I don't want to say ignore, but you kind of, brush a lot of the finer details under the rug. Right? And so what we can say is that, a systems level or high level type analysis, we're neglecting a lot of the finer details of the flow. Okay. Things like velocity patterns, things like vortices, things like that. Okay. Most importantly, to be a bit more specific about that statement, up until this point, we've basically been, for the most part, neglecting any spatial variations in fluid quantities. I guess to be even more specific, when you talk about spatial variations of fluid properties, most of the time you're talking about velocities. Okay. Let me just kind of illustrate this for you. So, when we're doing our control volume analysis and we're doing, let's say we're computing our inflow, outflow term and our Reynolds transport, right? For the most part, we assume that the velocity is constant along an entire inflow or entire outflow. Okay. All right. So for instance, let's say we have a control volume analysis like this, right? That's like an inflow and outflow just like this, right? We have flow coming in, flow coming out, right? So the way that we've kind of analyzed this type of structure here, or this type of system, is we said that at the inlet phase, we have just a singular velocity value, right? We call that V1, and the outlet has a singular velocity value V2, okay? And that velocity was uniform, or basically constant across the entire surface, okay? So implicitly, what we're kind of saying is that, if we were to kind of blow this up, and if you were to kind of, take kind of a magnifying glass across that outlet, right? So this right here would be our outlet channel, right? So we're just kind of zooming in here, right? What we're essentially saying is that across this entire surface here, our velocity is a constant v2 across that entire cross section. Okay. And so what we can say is that this velocity takes on what's called a uniform profile. Okay. All right, so for the purposes of control volume analysis, it didn't really matter all too much because again, we were looking at kind of the system as a whole, but if we were kind of interested in seeing, maybe the finer details of the velocity field at that outlet, we'd have to go a little bit more detailed because in reality, it is possible in some circumstances to have a uniform profile like this, but something like this actually technically is not possible. And when I say it's not possible, it's not possible in the sense that you would have velocity coming out of an outlet like that. That's fine. It's just that the velocity is never going to be perfectly uniform across the entire cross section. Okay. In reality, there's going to be variations, and so there'll be areas within that channel where the velocity is higher, and other parts where the velocity is lower. And there are some parts where the velocity actually goes down to zero. Okay. So a more realistic profile. That you can obtain by solving the Navier-Stokes equation would be to have like what's called a parabolic profile. Okay. Now I am going to rearrange some topics in this class just because Navier-Stokes is a little bit advanced, and so we'll probably save that until the very, very end if we have time. But what we're going to talk about this week kind of works our way up to that. Okay. All right. So in reality, you have what's called a parabolic velocity profile, which looks something like this. Okay, where the velocity is greatest in the middle of the channel, and the velocity actually goes down to zero at the walls. Okay. Right. So this is the parabolic profile. Right. If you want so there's a famous mathematician that first formalized the theory. His name is Poiseuille, and so this type of flow is often called Poiseuille flow. Okay. There's even a variation of this flow for cylindrical flow, which also has a parabolic profile, but is actually credited to both Poiseuille and his student. And his student was named Hagen. So it's called Hagen-Poiseuille flow. No relation to Haagen-Dazs ice cream. But that just happened to be what his name is. Okay. Okay. But the point of all this is that, is to say that, velocity profiles and velocity variations are a very important part of fluid mechanics. And we need different tools in order for us to solve for these types of variations. Okay. But of course, that begs the question of, why do we even care, right? So why do we even need to worry ourselves with the variations in velocity? What benefit does that give us as engineers? Well, so these variations in velocity actually give rise to a lot of very interesting phenomena. So one thing that we'll talk about at the end of class today. So if you've ever thrown a baseball, or if you're into baseball, you're probably familiar with the concept of throwing different kinds of pitches, right? So there's fastballs, there's curveballs, there's sliders, there's cutters, and the way the pitchers kind of create that movement, right? So the way that pitchers kind of take the ball, kind of do crazy things, is based on this type of theory here, right? And so the pitcher basically will generate spin. So not only will they throw the ball, they will throw the ball with a significant amount of spin, and depending on the direction and the speed of that spin, right, it causes the ball to do interesting things. And that theory is grounded in this type of analysis here. Okay. So specifically, that's called the Magnus effect. And so that's kind of the last thing that I have planned to talk about for today. But you can't analyze that, you can't do that type of fluid analysis without, these tools. Okay. Another example, just for my own research, is that one thing, if you're going to be analyzing, let's say, blood flow in the cardiovascular system, one quantity that's very important is what's called the wall shear stress, which is basically the frictional force or the frictional drag force that the blood imparts on the vessel wall as it's flowing past. And you can't compute wall shear stress without variations in velocity. Okay, and wall shear stress is important for other applications as well. Okay. So this, it's going to seem like, the tools and methods that we're doing now kind of bear no relation at all to anything that we've done up until this point, just because the math is going to be so different. But it is a very important part of fluid mechanics, and it's something that you need to know before we discuss. Right? I would say that for potential, the focus of today is going to be a subject called potential flow. That actually has a lot of applications in aerospace. And and I think it's even still used a lot today to design the shape of airplanes, airfoils, cars, things like that. Okay. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and move on. Okay. So before we begin, we do need to talk about conservation of mass again, but we need to talk about it from a different perspective. All right, so conservation of mass, obviously has been a big theme in this class. We've brought it up in multiple different contexts in multiple different ways. I think up until this point, we kind of understand conservation of mass as whatever comes in to a control volume, either it's either going to accumulate or it has to come out, right? That's kind of our understanding from Reynolds transport. But for this type of analysis where we're looking at more of the finer details of the velocity profiles, we need a different form of conservation of mass that's going to fit with the tools that we're going to discuss. Okay. Okay. And so specifically, what you're going to be seeing is that, instead of doing integral analysis, which is what we've been doing with control volumes, we're going to be doing differential analysis instead, right? Hence the name of this entire unit here. And differential analysis means derivatives and differential equations. Okay. And so instead of looking at conservation of mass in terms of a finite kind of, volume in space, we're looking at conservation of mass at a particular point, right? So at kind of one small, infinitesimally small location, how can we express conservation of mass at that small point? Because that's how differential equations work. So differential equations, have to be satisfied at every single location in space and time. And I realize that, Math 250B is not a prerequisite for this class. I know some of you are actually taking that class actually in parallel with this class right now. So that's why I don't want to get into Navier-Stokes unless we really have time at the end. Because, to really understand Navier-Stokes, we have to understand differential equations. But just to do this part, we're just going to need some of the basics. And so, what I'm going to show you is what's called the differential form of conservation of mass. Don't be too intimidated by it. It's at the end of the day, it is just derivatives, which you've already learned in calculus. And we're not actually going to be solving these differential equations. Okay. Okay. All right. So for an incompressible fluid, we can express the conservation of mass in terms of this partial differential equation, which acts on the velocity components. Okay. Okay, so we have partial u, partial x plus partial v, partial y plus partial w, partial z is equal to 0. Where u, v, and w here, those are the x, y, and z components of the velocity. Okay. Because remember, velocity is a vector, and so at every point, we have defined all three components in 3D. Okay. And so if you take the partial derivative of each velocity component with its matching coordinate direction, right? So you take the derivative of the x velocity with respect to x, derivative of the y velocity with respect to y, derivative of the z velocity with respect to z. You add all of them together, they have to equal 0 in order to satisfy conservation of mass. Okay. Okay, so this equation right here, this equation actually comes up quite a bit. It's used a lot in the Navier-Stokes, and so we actually give it a special name. Okay. So this equation right here is called the continuity equation. Okay. Right, so if you hear the term continuity equation in a fluid mechanics, perspective or context, then they mean conservation of mass. Okay. So again, this is a partial differential equation, and even in Math 250B, you don't, or even in 308, we don't learn about partial differential equations. So to actually solve this from scratch by hand is actually a little bit quite an ordeal. Partial just because you also need two other equations in order to solve for it. So we're not going to be using this as like a traditional equation where this is something we're going to solve for or plug in for it. But it is something that we're going to use to develop theory. Okay. Okay. And I say that because, we also need the continuity equation in polar coordinates as well. Okay. So this is the continuity equation in Cartesian coordinates, x, y, z. So that's, I think, the coordinate system that most people are familiar with. But just to develop a tensor flow, we also are going to need polar coordinates as well. Or I guess more specifically, cylindrical coordinates. And again, don't be alarmed. I know this expression looks intimidating, but we're not actually going to be solving. We're not actually going to be solving this equation. We're just going to be using it to develop our theory. Okay. Okay. So in cylindrical coordinates, our continuity equation looks like the following: get 1 over r partial r of r u sub r plus 1 over r partial theta of u theta plus partial uz partial z is equal to 0. Okay. All right. So this is the same equation. It's just that we've changed our coordinate systems. We've changed our perspective in terms of how we're evaluating. Okay. So in this case, u theta, and uz. Those are the same three velocity components, except that instead of being in terms of x, y, z, we have them in polar coordinates. And so that's the velocity in r direction, in the theta direction, and the z direction. Okay. Okay. So the way that we're going to use these continuity equations is essentially if we're given velocity components, and so we're going to have expressions or functions for the velocities, either u v w or u r, u theta, u z. And so if those velocity components satisfy these equations, then they satisfy conservation of mass everywhere within the flow. Okay. All right, and so this part here, this is going to be the most important part. So I'm going to pause. Okay. So what you're going to see, as we kind of go throughout the rest of the lecture today, we're going to develop this idea of potential flow, which involves things like stream functions and velocity components. At any point, we can take that theory or we can take where we're at and plug back into these continuity equations. And if we plug back into the continuity equations and they are satisfied, and so essentially we take the partial derivatives, we add them up, they equal zero, then we can say that our conservation of mass is satisfied. Okay. And out of all the conservation law, I mean, all the conservation laws are important. So there's no conservation law that's more important than the others. But always the first one that we check is always going to be conservation of mass. So that is the baseline for any type of viable physical flow situation. Okay. And so most of the time, when you're developing any theory in fluid mechanics, you're starting with conservation of mass. And so we'll be coming back to these equations. And if we have time for Navier-Stokes by the end of the summer session in 2 weeks, then we'll be returning to these as well. Okay, so definitely keep these in mind. All right, any questions on this so far? Okay, good. All right, so today, today's lecture will be, a kind of a little bit of a contrast from the last two. Not really too many examples today. We're just kind of developing and introducing the theory because this is kind of a newer topic. So just kind of be prepared for that. Okay. All right, so the next concept that we're going to introduce is the concept of a stream function. All right. So stream functions really kind of form the basis of potential flow, right? And so it's kind of important for us to kind of understand what they are. Okay, but before we kind of introduce that idea, let's kind of limit ourselves, and let's say that from this point forward, we're only going to concern ourselves with two-dimensional flow. It's not that 3D flow doesn't exist. It's just that 3D flow just adds a lot of complications and a lot of details that frankly aren't really necessary for understanding the theory. And also 3D flow is very difficult to draw. So 2D flow still kind of difficult to draw, especially with someone with two left hands like me. But it'll be a lot easier to draw for 2D flow. Okay. And so under 2D flow, our continuity equations, they do take a different form. Right, and so the main difference is that we are going to neglect the z direction in our continuity equations. Right. And so our continuity equations take the following form. So we're gonna focus on the Cartesian one first, but we are going to come back to this to the polar coordinates in a bit. Okay. So in Cartesian coordinates, we have partial u partial x plus partial v partial y is equal to 0. Right? And then in polar coordinates, we have the following. So we're just going to eliminate the last derivative there. So in polar coordinates, we have 1 over r, partial r, r u r, plus 1 over r, partial theta, u theta is equal to 0. Okay. All right, so it just makes our lives just a little bit easier. Okay. All right, so again, we're focusing on the Cartesian form here, right? We have kind of an interesting kind of situation here, right? So we're taking the sum of two different partial derivatives, okay? And in order for conservation of mass to be satisfied, the sum of those two partial derivatives has to equal 0, okay? So let's do this. And so, just because, it is a little bit cumbersome to always have to worry about two different velocity components, let's try to come up with a single function that we can use to satisfy continuity. Okay. Okay. And so, somewhat kind of skipping a lot of the details of the derivation. So we're just gonna pull this out of our ass. And so we're gonna say we're going to define a new function. Okay. Which we will define as psi. And so the symbol for psi kind of looks like Poseidon's trident. Okay, so that's a psi. Where this psi function here will be closely related to the velocity components. Okay. Okay, and so what we can say is that, if we want to take our function psi and we want to get the x velocity, we can take the derivative of psi with respect to y, partial derivative. Okay, so we can say that u is equal to partial psi, partial y, and v is equal to negative partial psi, partial x. Okay. Right, and so the psi in both of those partial derivatives are the same psi, right? So if we define the function psi in a certain way, and we take these partial derivatives, we can obtain the velocity components from them, okay? Now, this is very intentional, right? Because, let's take these two expressions and let's plug them back into continuity. Okay, so continuity is what I have boxed in green up there. So it's partial u partial x plus partial v partial y. Okay. If we take these expressions for u and v and we plug them back in, let's see what we get. Okay. So let's take u and plug it in here, and then we'll take v and plug it in right here. Okay. Okay. So we're gonna have partial x of u, which is partial psi partial y, plus partial y of v, which is minus partial psi partial x. Okay. All right, and so we're going to check and verify that if we define psi in this way, that it does satisfy continuity. Okay. Okay, so we have these two terms here. We have to evaluate their derivatives. And so for both of these terms, we have a cross derivative. Okay. So first term here is going to be partial squared psi, partial x, partial y. Okay. For the second term there, the negative is going to come out in front, so we have a minus. Partial squared psi, partial y, partial x. Okay. Okay. Now, the thing about partial derivatives, if you remember from Calc 3, is that they are commutable. And so that means that it doesn't really matter which order you take the derivatives in, you get the same answer. Okay. And so this second term, or the first term, you can rewrite either of them. And so this term is actually equivalent to partial squared psi, partial x, partial 1. Okay, so it doesn't really matter which order we take the derivatives in. Okay. And so if we make that substitution there, we have partial squared psi, partial x, partial y, minus partial squared psi, partial x, partial y. Those two are the same. We subtract them, they equal 0. Okay. And so what we can say is that if we define psi in this way, okay, if psi is defined in this way, then its velocity components will satisfy continuity. Okay. All right, and so this psi has a name, right? And probably you can already guess what the name is because it was spoiled by the title of this section. So this psi is what we call a stream function. Okay. So we're going to use this concept of a stream function throughout, right? But the whole idea of the stream function is that the stream function is a scalar function, right? So that's kind of another benefit of that is that you don't have to worry about different vector components. But the stream function is as a scalar function that's defined in a way, if you take the partial derivatives of the stream function and set those equal to the velocity components, then you automatically kind of satisfy the continuity equation, which is very beneficial. Okay. All right, any questions on this? Okay, all right. So let's do a quick example. So let's see how we can actually solve for this stream function. Okay, so this example here is not typical. So this is not an example of, this is like a problem I would give you, but this is kind of more of like a like an illustrative example, so you can kind of just to understand the stream function a bit better. Okay. Okay, so let's say that we have a velocity field. And let's say our velocity field is given by the following components. Okay. So we have u is equal to 2y, and we have v is equal to 4x. Okay, so in this problem, we're just given the velocity components right away. So let's do two things with this example here. Okay. So A, based on these velocity components, let's verify that the continuity equation is satisfied. So that's going to be pretty easy to do. So all we have to do in that case is just plug these velocity components into our continuity, and then we should get 0 from doing so. Okay. And then once we do that, and of course, spoilers, it does satisfy continuity. So part B, once we verify that this satisfies continuity, let's solve for the corresponding stream function for this flow. Okay. Okay, so pretty straightforward, but I think this will be kind of our first kind of hands-on experience with the stream function. All right, so let's do part A. So part A, we're just going to verify continuity. So continuity for a 2D flow, we have partial u partial x plus partial v partial y, right? We plug in for u and v, and that should equal to 0. Okay. Okay, because we have our expressions for u and v there given to us in the problem. Okay. So first, let's plug in u. So u here is 2y plus v, which is 4x. And if we do that, then that should equal to 0. All right, so let's go ahead and take these partial derivatives, right? And so we have first a partial derivative with respect to x of 2y, okay? So even though y here is an independent variable, it does not depend on x, right? So this whole term actually is going to go to 0. Right? And the reason being that there's no x in the u, right? So the u is 2y. And so when we take the derivative of partial derivative with respect to x, y here essentially acts as a constant, right? And so taking derivative of a constant gives us 0, right? Same thing for the second term here, right? And so when we take the derivative of 4x with respect to y, when we're taking the derivative with respect to y, x here kind of essentially acts like a constant because it's not a function of y, okay? So this also is equal to 0, because there's no y dependency. And so overall, we have 0 plus 0, which of course is 0, right? And so this tells us that continuity equation is indeed satisfied. Okay, good. All right, it's very straightforward, right? So remember, for continuity equation, again, we're not going to be solving for it, but we are going to use it in this way. We're going to plug in, velocity components for string functions, and just to verify that our conservation of mass is indeed satisfied. Okay. Now let's go ahead and solve for the string function. Okay. Where string function is psi. Okay. Now to solve for psi, we're going to make use of the formulas that relate our velocity components to our string function. Okay. In particular, right, we have the formula that u is equal to partial psi, partial y. Okay. And v is equal to minus partial psi, partial x. Right, so for both of these cases, we're going to plug in what we know for u and v and simply integrate in order to solve for psi. Okay. All right, so for u, let's do that first. So u here, we know from the problem is equal to 2y. Right, so that tells us that 2y is equal to partial psi, partial y. Right, so let's go ahead and take the integral of both sides with respect to y. It should be dy. Okay. All right, so that integral with respect to y is going to cancel out y on the left-hand side. So on the left-hand side, we're just left with psi. Okay. And on the right-hand side, we have integral of 2y with respect to y. And so that's going to give us y squared. Okay. But since we took the integral with respect to y, right? Psi is even though it's a scalar function, psi does depend on both x and y, and so we do have to add an arbitrary function to this. Okay? All right, so don't forget this. Right, so remember, whenever you're doing an indefinite integral, which is an integral without any bounds, right? So there's no upper and lower bound. You have to add a arbitrary function to this. A lot of times it's an arbitrary constant. But when you're taking integrals of partial functions like this or partial derivatives, whatever function that you did not integrate on, that's going to be your unknown constant. Okay? which in this case, since our function psi here is both a function of x and y, we only integrated over y. That means we're going to add an arbitrary function of x, f of x. Okay. Okay. All right. So let's go ahead and do the same thing for v. Right. So we need to integrate both in order to get solve for psi. So for v from the problem, we know this is equal to 4x. Okay. So once again, let's go ahead and integrate. This time we're integrating with respect to x, because that is our derivative term, right? So you're going to take the integral on the same variable that you're taking the derivative of. Okay. Okay, so integral of the left-hand side, what we get is negative partial phi partial x, integrate with respect to x. That's minus psi. Okay. And on the right-hand side, we have integral of 4x with respect to x, which is 2x squared. Okay. And just like the other part, we are going to add an arbitrary function of y in this case, because we integrated with respect to x. Okay, so that's going to be equal to g of okay. All right, and so we have two different expressions here for psi. So psi is equal to y squared plus some arbitrary function of x, and then let's go ahead and move the negative over, right? And so from the other side, we have psi. That pencil turned off. Psi is equal to minus 2x squared plus g of y. Okay. Since g of y is so arbitrary at this point, technically that negative should go there too, but we haven't defined g of y, so we can just say we absorb the negative in there. Okay. Okay, and so from here, hopefully the answer should be pretty obvious because, we have two different expressions for psi, right? One expression which has the arbitrary function of x, but if we look at the other expression for psi, we have a term here that is just an arbitrary function of x, which is minus 2x squared, okay? And then our other expression for psi, we have an arbitrary function of y, and you can see that matches up with y squared, which is this function. Okay, so we combine these two, we get psi is equal to y squared minus 2x squared, right? So we just kind of merge those two ideas together. But we also have to add an arbitrary constant. Okay. So even though we've plugged in for the arbitrary functions of x and y, a stream function most of the time is only arbitrary up to a constant. Okay, and the constant is actually very important, and we'll discuss that in like 20 seconds. But before we get that, are there any questions in terms of how we got this result here? Okay, good. Okay, so let's go ahead and write that down. Okay, so that's important to note that stream functions are always arbitrary up to some constant. Okay, and the constant is actually important because, first of all, one way you can see it is that the whole purpose of the stream function is to get the velocity components u and v, right? And in order to get u and v, you have to take derivatives of the stream function psi. Okay, and whenever you take a derivative, so let's say you take a derivative of psi with respect to x or with respect to y. In both of those situations, the arbitrary constant c is going to go away. Okay, and so in some sense, you can say, we don't really care if there's a constant there because it doesn't really affect our velocity contributions. Okay, but that constant does actually play a role. Okay, because the stream function actually has another interpretation or another function on top of just being a vehicle for the velocity components. Okay. And it's related to the idea of a stream line, right? So I know, in terms of actual time, it hasn't been that long. So I think maybe it was like 2 weeks ago. But in terms of course time, the amount of lectures that have been done, it was a while ago, right? So remember, let's kind of remind ourselves what a streamline is. So a streamline is a basically a visual guide for us to kind of see which direction the flow passes through in a flow field. Okay. So a streamline is a path through a flow. It's a path through a flowed velocity field where everywhere along the streamline it is tangent to the velocity field. Okay. Okay. So I think I brought this up, when we first started talking about flow kinematics. But they're going to play a bigger role here. Okay. Because the way stream functions and streamlines are related, and they both use the word stream on purpose, right? And so what we can say is that lines of constant psi correspond to the streamlines in the flow. And in fact, you can hop from one streamline to the next within the flow by just adding an arbitrary constant to your stream function, right? So if you have a stream function, y squared minus 2x squared plus 1, right? Versus psi is equal to y squared minus 2x squared plus 2, that's going to give you a different streamline. It's all going to be within the same flow, right? And so we're still going to be satisfying conservation of mass. You're just following a different pathway through the flow, okay? So that arbitrary constant there in our stream function allows us to plot out different streamlines within the flow, right? And a lot of times, if you're trying to visualize a flow, you get to kind of more advanced flow visualization. That's one way that you can do it. Is that you just plot different streamline contours. Okay, so that's kind of what they're called, streamline contours, stream function contours. Okay. All right. Any questions on this? Okay. All right. So now that we've kind of gotten all the preliminaries out of the way, right? So we kind of understand kind of what we're doing here. We're now trying to develop a tool set to solve for detailed velocity fields. Now that we also know this concept of continuity, we know this concept of stream functions. We can actually start to apply it in what's called potential flow. Okay. So potential flow has its roots in aerospace design. Some people would kind of say it's kind of an old school way of kind of doing it. This was kind of developed before the age of high performance computing and computational fluid dynamics. But in order to kind of model and kind of visualize and illustrate kind of the complex flow patterns around, let's say, an aircraft or something like that, potential flow is used. Okay. And even though I would say nowadays we do have very advanced tools for simulated flow, potential flow does still have its use. Because if you really understand potential flow, it is a very elegant and very efficient way to develop these kind of streamlines. Way faster than CFD, right? So computational fluid dynamics is, and I'm a CFD guy. That's kind of what I do for my own research. But and so I'm one of the biggest cheerleaders for CFD that's out there. But even I know that there's a time and place for that. And potential flow, not only just from a historical perspective, but just from a practical perspective, still has its place just because it is so efficient. Okay. Okay. So the whole idea with potential flow is that we're basically going to take different stream functions from different types of flow phenomenon and combine them together to create complex flow patterns. And so in some sense, potential flows it's kind of fun in a way because you can kind of combine different stream functions together and kind of see what the combination kind of what works out to, right? When I was in college, there was one of the labs that we did in terms of a fluids lab was there's a very rudimentary program, and these were run on kind of 1970s computers, where basically you can take different stream functions, you can add them in, and you can visualize, you can kind of see exactly how it's going to change, what's going to happen. And that was really cool, right? And so I don't think we have that now. But you can kind of see the theory and potential kind of behind it. Okay. Okay. So what allows us to do this? Or how can we just combine string functions, right? Or what does this even mean to combine string functions? So that's kind of a vague kind of phrase there. Okay. So let's talk about that first. And so in order to combine string functions, we do have to impose an additional constraint or an additional conditions on our string functions. Okay. And that is something called irrotationality. Okay. All right, so I'm just going to go through this a bit quickly, just because the roots of this derivation are kind of more. It's kind of more in calculus a bit more. But if you kind of remember from Calc 3, there's this concept of a curl, right? Okay. So the details of a curl operation, for this class are not too important, so I'm not going to dwell too much time on it, but I will kind of outline the basic steps. Okay. So the curl, basically you're going to take the cross product between our velocity field and this operator, which we call the nabla. Okay. Right. So this operation right here is called the curl of our velocity field. If you get more advanced fluid mechanics, let's say you go for a master's degree and you take more advanced fluids, this expression here will become a lot more relevant. You go into a lot more detail. But for today, all you really have to worry about is that for irrotationality, this curl has to equal 0. Okay. All right. And then, if you basically take this requirement of irrotationality and, for our velocity field here, we plug in our string function representation. Right, you do a little bit of math, not too much, but you end up with the following partial differential equation, which looks similar to our continuity equation, but just notice that it's on our stream function instead. Okay, and so we end up with the following equation. We get partial squared psi, partial x squared plus partial squared psi, partial y squared, which is equal to 0. Okay. Okay. So this partial differential equation, again, we're not going to be solving it, but it is the fact that we got this result is actually significant because this form of differential equation is actually a very special type of equation. So mathematically, this is what's called the Laplace. Again, named after the famous mathematician Laplace that formalized the theory. Okay. That is one of my pet peeves about just science in general. It's just that, all of these ancient mathematicians, they discovered some theory and they named it after themselves. Which, if you just told a random person what the Laplace equation is, you would have no idea because the name is not descriptive in any way at all. but that's everywhere. So there's Bernoulli's equation that's named after Daniel Bernoulli, the guy who discovered it. Um, and I guess it is a great contribution. You can name it after yourself, but it is annoying to learn for sure. Okay, so what's special about the Laplace equation? So Laplace equation itself, we actually can solve this in the realm of partial differential equation. This one's easier to solve than most. But the only thing that we really care about is that this is what we call a linear equation. Right. And so for the very first time, right? So, up until this point, we've only really defined psi in terms of its velocity, right? In terms of how it transformed into velocity. But this is the first time we actually have an equation that psi itself has to satisfy. Okay. We already know that the velocity components, they have to satisfy continuity, but by imposing this requirement of irrotationality, we also now have an equation that psi itself has to satisfy. Okay. And the fact that our psi here it follows a linear equation means that we can combine different solutions of psi together through superposition. Okay. So when I mentioned, 5 minutes ago that, we can combine different size solutions to create complex flow, what I mean by that is we can use superposition, okay? And superposition is a very, very fancy word for a very, very simple operation. Superposition, all that really means is that, we can take two different psi solutions where we know that each, let's say psi 1, psi 2 are both valid. By superimposing them, we just simply add them together and we say that their sum also is still a valid stream function. Okay. Okay. And so that's just a very fancy way to say, let's say psi 1 is a valid stream function. Right? And so it satisfies continuity, is irrotational. Okay, so same for psi 2. Okay. Right, so psi 1, psi 2 are both valid stream functions. And so by superimposing them, what we can say is that we can define a new stream function psi 3, okay, which is just the sum of psi 1 and psi 2. Okay. And by the principle of superposition, we can say that psi 3 is also a valid stream function, since psi 1, psi 2 were also both valid stream functions, right? So you add them together, you still get something that's valid, okay? It's valid and probably more complex than it was before. Okay. All right, so I know I went through that very quickly, but it's one thing where I didn't want to dwell too much on the details of the derivation, just because the more interesting part is kind of yet to come. But this a lot of the things I kind of brushed over now, they are kind of very interesting, and especially if you do have if you do plan on either pursuing a graduate degree or pursuing just fluid mechanics in general more, throughout your time here or maybe throughout your career, I would definitely go through those details. So they are quite important. Okay. Okay. Any questions on this so far? Okay. All right. And so for the next hour or so, we're going to be kind of doing kind of the same thing. So basically, now that we kind of established these rules for psi, and we know that we can just combine them together by adding them together, right? We're going to introduce what I call kind of the basic flow, the basic building blocks of potential flow. And so what I mean by that is that we're going to introduce, fairly basic flow patterns along with their stream functions. Okay. With the idea is that, later on, we're going to be combining these basic building blocks together by doing superposition to create more interesting kind of flow patterns. Okay. Okay. All right, so that's basically the idea with potential flow. So the idea with potential flow is to use these basic building blocks, use these basic flow patterns, take their stream functions, add them together in kind of really interesting ways, and then you can use that to create some very interesting and complex and realistic flow patterns. Okay, so I have four building blocks that we're going to go over. I believe. Can you just double check that? The uniform flow, sync, vortex, and the delta it should be. Yep. Okay, so we have four different types of basic flow patterns. And so we will go through them all together and then we will see how they combine together. And that's kind of when stuff will start to get a bit interesting. Okay. Okay, but before that, let's go ahead and take a break. We're going to take a break a little bit early today just because I'm parched. I need a drink of water. So let's come back at 4:20 and then we'll continue on with this. Okay. Okay.
Just in one.
Okay.
Machine.
Okay.
So you get number.
Oh, yeah. No worries.
Thank you.
Yep.
Definitely about 40 something. Longer than that.
All right, it's 4:20, so let's get back into it. Okay, so before the break, we introduced this idea of a string function, and now that we see that we can combine them together by simply adding them together, now what we can do is we can introduce these, what I call, basic flow building blocks. We'll introduce their string functions. We can add them up together, okay? And then after we introduce these basic building blocks, we'll do a couple of examples where we kind of see what the combination looks like. You'll see that the combinations are more intuitive than you think. And then we'll kind of do some application from them as well. Okay. All right. But first step is just to start introducing these basic building blocks. So let's start with the simplest one of all, which is called uniform flow. Okay. So uniform flow, as the name implies, is a velocity field that is uniform everywhere. Okay. It is a flow that is going in one direction. Okay. All right, so of course, this flow is a bit ironic because we started today by saying that this doesn't appear often. Okay, so uniform flow is possible. It's just a lot of times it's possible in situations that are far away from surfaces. Okay, so in the context of a control volume, usually a control volume we're bound by solid walls. It is hard to get uniform flow in that situation, but if you have a situation where you're far away from any kind of solid surfaces, uniform flow is very common. Okay, so think about atmospheric winds, right? So like wind in the atmosphere, it's far away from any kind of it's far away from the Earth's surface. There's for the most part airplanes and stuff flying everywhere in the air, and so if you have a wind pattern, usually the flow pattern is uniform. Okay. Okay. So the direction of the uniform flow is all going in one direction. In this example, it's going in the positive x direction, although it doesn't necessarily have to do that. Okay. The magnitude or the speed of the flow is given by u. Okay. Okay. All right. And so in this situation, at least in this configuration here, our velocity components are very easy to determine. So our x velocity, little u, is equal to u, right? Little u is equal to big U. And in this situation, we actually have no velocity in the y direction, so little v is 0. Okay. All right, so we can go through the same exercise as we did before. So we can take integrals of these to come up with a stream function. You can definitely do that in your spare time, but in this case, it's pretty straightforward. And so our stream function for uniform flow is simply equal to big U, the speed, multiplied by y. Okay. Okay. All right. And so, like I said, it is possible to get uniform flow in other directions. One very obvious one is you can get uniform flow in the y direction. And so in that case, our stream function will be u times x, or excuse me, minus u times x. But for our purposes, we're only going to consider flow in the x direction. Okay. Okay, the uniform flow, very straightforward. The simplest one that we can do. Stream function also very easy to do as well. Okay. And unfortunately, this is going to be the only stream function that's going to be in Cartesian coordinates. All other stream functions that we are going to go over today will be in polar coordinates. Okay, so just kind of be aware of that. Okay, any questions on uniform flow? Okay, all right. So we're just going to go kind of rapid fire with all these different building blocks here. Okay. All right. So the next one, technically it's two, but they both have the same functional form. So we're gonna consider them together, and so that is a source and a sink. Okay. All right. So a source and sink is characterized by flow that is purely radial. All right, and we can have two different types of radial flow. So we can either have flow that is either going towards the origin or flow that's going away from the origin. All right, so visually it looks like the following. So we have our Cartesian system here. All right, so we have our origin here, right? And so purely radial flow means that we have flow that's going, if you imagine, draw a circle here. Okay. Right. So the radial direction is a direction that goes from the origin out to the extremities of the circle. Okay. It's a little bit, you have to kind of form your mind in polar coordinates, right? So you can't think of this in Cartesian. And so the radial direction, right, is one that goes from the origin out towards the surface. Okay. So all of those arrows that I drew there, because they go from the origin out towards the surface, those are all radial velocities. Okay. In other words, we only have just pure UR. Okay, so U sub R is the velocity in that radial direction. Okay. Continuing along with that polar theme, that means that U theta, actually let me use a different color for theta, U theta. Okay. U theta in this case is going to equal to 0. Okay, so we're going to have no polar direction flow. Okay. We'll go over polar direction flow in a second, but U theta is going to be any direction that goes along the perimeter or along the circumference of the circle. Okay. So U theta would be, velocity in a direction kind of like this. Okay. Now, we're not considering that in this case, but I just want to kind of illustrate to you the difference between radial flow and polar. Okay. Okay. All right. And so the way we're going to define the source and sink is like the following. Okay. And so we're going to define it as the following. So we're going to say UR is equal to okay, minus M divided by 2 pi R. Okay. Right, where our parameter of choice here is M. Okay. M here is what we call the strength of the source. Okay. Or a sink. So it's a sink in this case, but because I put a negative sign. So I know, sorry, it's a bit confusing. I know in the figure I drew a source because the flow is coming away from the origin, but the negative sign there means that we have this for a sink. Okay. Okay. All right, and so if we relate this, and so just like we did with the uniform flow, let's solve for the stream function that's associated with this velocity field. Okay. And so let's use our relationship between stream function and our velocity components in polar coordinates. And so we have UR is equal to 1 over R partial psi partial theta, which is equal to, oh sorry, and then u theta is equal to minus partial b partial r. All right, and so if we use the fact that UR here is equal to minus m over 2 pi r, and we use the fact that u theta for this case is equal to 0, okay? So that gives us our two equations that we need to solve for psi, right? So just like we did in our first example today, we're just going to integrate these velocities with respect to r and theta, right? And then what we get is psi, which is a function of r and theta, for source and a sink is equal to plus or minus m divided by 2 pi times theta. Okay, so that right there is our stream function for a source and a sink, right? The only difference is that for a source, we're going to have a positive m, and a sink, we're going to have a minus. Okay. Okay, and so you can kind of see why we're introducing polar coordinates here. So if we were to try to define the source or a sink in terms of Cartesian coordinates, just because of the nature of the radial flow, it's not like uniform flow where it's constant in either x or y. The radial direction technically has components in x and y at different locations. And so it is possible to compute the stream function in Cartesian coordinates for a source and sink. But trust me when I say that this form here is a lot easier. And I say that just because, even myself, I had hesitations working in polar coordinates just because it's, honestly, I think it's just because we don't get enough practice doing it in our math up until this point. But this is one situation where the polar coordinates is much simpler. Okay. Okay. All right. Any questions on the source and sink? Okay, all right. So before we move on to the next type of potential flow building block, I do want to call your attention to one really interesting detail here. Okay. And so you can kind of see, the reason we have this is partially just because of how the polar coordinates are defined, right? And so if you look at our expression for UR, you'll notice that there is a R in the denominator here, right? And so on the one hand, you can say that, okay, that 1 over R corresponds to this term right here, right? So when we're computing velocity, there just has to be a 1 over R there just to match up with the polar coordinates. And in some sense, that's true. But, it also creates a very interesting situation, okay? Because if you look at our figure here for our source and sink, right? You'll see that the origin is actually part of our domain, right? So the origin is not something we explicitly exclude from the source or sink, okay? And what's unique about the origin? So at the origin, our radial coordinate r is actually equal to 0, okay? Now, why is that an issue, right? And so if our origin is part of our domain, that means that our radial velocity, right? We plug in r is equal to 0 there, right? We get minus m over 2 pi times 0. And just we know from math that any number divided by 0 is essentially infinity, or technically it's undefined. Okay. And so what we can say is that our source and sink is actually undefined at the origin. Which is quite odd, right? And so it's this flow field, it has a location where our velocity is undefined. It might be infinity. Everywhere else, actually, everywhere else it's fine, right? So everywhere else we have a clearly defined velocity field, it's fine. But at one very particular location, we are not fine. We end up with something that's not physical. Okay. And so this type of situation is called a singularity. Okay. So everywhere else, we have a clearly defined velocity field, but just at one particular location, we have a singularity. Okay. And unfortunately, there's not much we can do. The only thing we can really do is just avoid the origin. Okay. Which sounds weird to say in a mathematical situation, but once you see that, once we start combining these flow situations together, you'll see that it is actually possible to avoid the origin. We just have to kind of hide it in a very kind of clever way. Okay. Okay, so kind of keep that in mind because all the rest of the potential flow building blocks that we're going to cover does have a singularity, and in fact they're always at the origin, and so just kind of be aware of that. Okay. All right, so the next type of potential flow building block that we're going to go through is what's called the free vortex. Okay, so the free vortex, in some ways, you can consider that is the free vortex is considered to be kind of the opposite of a source or sink. Okay, so unlike the source or sink where we had purely radial flow, a free vortex is purely polar flow. Okay. Okay. And so for a free vortex, we have UR is equal to 0, where U theta is non-zero. Okay. We'll go through what that expression is in a second, but let's go ahead and draw it first. Okay. So a free vortex looks like the following. Right. So remember, U theta is a direction of flow that circles around the origin. Okay. Okay. And so all of the U theta is going to look like the following. Okay. So I'm just going to draw particular contours here, but the U theta is defined in all other locations as well. Okay. Right. So for a vortex, just kind of like the name implies, a vortex is going to be spinning around the origin. Okay. You can keep going, but it's a little bit obnoxious to keep drawing these arrows here. Okay. Okay. All right. So the stream functions for this, we can go through the same exercise we did for the previous one, but this time let's start with the stream function itself. Okay. So the stream function for a free vortex is given by the following. Is going to be this symbol here, which is a capital gamma, okay, multiplied by natural logarithm of r divided by 2 pi. And once again, we can have a positive or negative here as well. Okay. Where in this case, the positive or negative tells you what the direction of the vortex. Okay. So a positive stream function here will have a vortex that's going in the counterclockwise direction. A negative vortex will put a vortex in the clockwise direction. Okay. Okay, and so just like the source and sink, we do have a key parameter here, which is the this capital lambda here. Okay. Or gamma. I always forget which one's which. Okay. But this parameter here is what's called the total circulation of the vortex. Okay. Where you can think of circulation as being defined as the strength of the vortex. So, the more circulation you have, the stronger the spinning is going to be, the higher your velocities are going to be as well. Okay. Okay. So hopefully you kind of start to see a theme kind of develop here as well. So for all of these stream functions, there's a single parameter within the stream function itself that kind of characterizes or describes the strength of that stream function. So how much velocity or how fast it's going to be. Okay. Okay, and then from this we can also determine the velocities, which in this case the only velocity that's going to be relevant is velocity in the theta direction, the polar direction. Okay, so u theta is going to be, if we go back to our equations from before, it's going to be minus partial psi partial r. Okay, and that's equal to our circulation divided by 2 pi r. Okay, or once again, where we have this issue here, where we have undefined kind of flow at the origin of our domain, right? So we have the same 1 over r here. So r is equal to 0, or the origin is also another singularity. So if we're going to use a flow with a vortex, we need to avoid the origin in our analysis. All right. Any questions on this? Okay. All right. One more building block, and then we'll start to do some interesting things. Okay. So the last building block type flow is actually kind of it's technically our first example of a combination, but it's used so much that it kind of has its own stream function, right? And so this last type of flow is called a doublet. Okay. So the doublet, technically, the way that it's defined is actually the combination of a source and a sink together. In fact, the way that it's defined is actually quite funny, and it's kind of described this way in every fluid mechanics textbook, right? But so the way you get a doublet is you take a source and you take a sink, right? And you start them kind of far apart. Right? So in here we have a source, and a source we know we have flow that's radiating outwards from it. And then we're going to take a sink. Okay. And a sink is the opposite. It has purely radial flow, but instead of flow radiating out, we have flow that's coming into the sink. Okay. Right, and of course these are obviously offset, right? And so these are obviously both not at the origin, right? We are going to bring them close together. And so, it's kind of just a funny picture of just, two things that don't agree and just kind of force them to be together in the same room, all right? But even apart, this starts to form some very interesting flow patterns, right? Because obviously you can see that flow is going to come from the source, right? And then it's going to come from the source and then flow into the sink, right? And so you have a bunch of streamlines that actually kind of go just like this. Okay. So you have this kind of like rainbow effect where, you have flow that's coming from the source and going to the sink and making these kind of arches in the flow. Okay. Now, if you take this situation and you bring the source and sink closer together until they both converge at the origin. Okay. Right, so we're basically going to layer these two things on top of each other. And so on the one hand, you might think that putting these two together in the same place is going to cancel them out. And in some sense, you're right. There is no net flow here. Okay. But those interesting arch patterns will still actually be maintained. They'll be maintained and they kind of converge and kind of snap to a circular shape. Okay. And so the flow patterns that come out kind of look like the following. Okay, so we have our coordinate axes here, right? And so those arches that we kind of saw from the previous figure, they kind of come together and they kind of form a full circle instead, okay? So we have a circle that kind of forms on the top, just like this. Flow is kind of going around, kind of clockwise around that circle. And then same thing on the bottom, right? So on the bottom, we also have kind of a circle down here, okay? And flow is going this way, okay? And then this kind of extends outward as well. And so we have kind of this, almost like a figure eight that kind of forms. And then this figure eight kind of radiates further and further outward. Okay. And so we have another kind of flow contour that kind of looks something like this, right? Okay, so kind of like a bigger eight. And there's kind of a bigger eight kind of around that as well. Okay. And then eventually, you get far enough away such that, that arch doesn't form, right? And so you'll have flow patterns that kind of come out like this, out like this, out like this. Okay. All right, so really interesting kind of flow pattern. And you'll be surprised that when you combine this doublet together with other types of flow, especially the uniform flow, that's when things start to get kind of interesting. That's how you get flow around a cylinder. Okay. Okay, and so what does the stream function look like for a doublet? And so for the doublet, just because it is its own special thing, now technically you can get this by just summing together a source and sink. You have to do it kind of in a clever way, otherwise you kind of get to zero. But because the doublet's kind of its own interesting thing, it has its own unique stream function. Okay, so the stream function for a doublet is given by the following. So you have psi is equal to minus k, or plus or minus k, excuse me. Sine of theta divided by r. Where once again we have a strength parameter here. It's not as straightforward as the source or sink or the uniform flow. K here is just a generic doublet strength parameter. Okay. Okay. But you can increase the strength of your doublet, which is kind of increases the velocities of the flow patterns by increasing that value K. Okay. All right, and so those four flows, we have uniform flow, we have the source and sink, we have the free vortex, we have the doublet, right? So those are the four, I would say, basic building blocks for potential flow. It's at least it's enough for us to get started in combining. Okay, so there are other building blocks as well. You pick up any fluid mechanics textbook. There's more out there. But at least just for a basic understanding, I think this is a good place for us to stop. Okay, because even with these four, we can do some kind of really interesting things. Okay. All right, but before we do that, I do want to make just one observation here. Okay. Okay, so I mentioned this kind of back when we talked about uniform flow, right? So all of these potential flow solutions, they all kind of rely on the same assumption where we have a completely free and unimpeded flow field. Okay? So in other words, there's no solid surfaces here that we can use to impede the flow. Okay. Now we can create some solid surfaces based on our patterns here, but there's nothing external. There's no external solid surfaces that are going to impede the flow. Okay. Now that has a very important consequence, and that important consequence is that all of the flows that we're considering with potential flow will be inviscid. Okay, so there's going to be no viscosity that's going to be. So we'll learn this in probably the last week. And so this might be either the Tuesday or the Wednesday right before we take the final exam. Viscosity does play an impact in these types of flows, but the effects of viscosity are limited to a very small region, usually very, very close to a solid surface called a boundary layer. Okay. Boundary layers are extremely interesting. In fact, there's a ton of research that goes into studying boundary layers. And even still, there's still, I think, a lot that we can understand more about them. They are very advanced, and so we're not going to talk about them too much in this class. But boundary layers are very, very important for fluid mechanics. We'll touch on them probably a little bit near the end, but let's just kind of name that. But boundary layers are kind of the only regions in a free flow field like this where viscosity kind of becomes important. Okay, so for the most part, we're going to assume our flow is inviscid. Okay, but because our flow is inviscid, that actually unlocks something else for us, right? Because what is the other theory that we went over in this class that assumed inviscid flow that we kind of made a big deal out of? Bernoulli's equation, right? Now, of course, Bernoulli also depends on steady state and involves on incompressibility. It depends on if you're following a streamline. But if you think about it, all of those conditions are satisfied here in potential flow as well, right? So from the very beginning, just based on our form of the continuity equation, we've already assumed that our flow is incompressible. We're already assuming steady state just because we're not considering any time dependency. And following a streamline usually is not that difficult. Okay. So actually with potential flow, the really interesting parts are combining together what we're going to do with the stream functions. And we can actually use Bernoulli in combination for this to actually solve for pressure distributions as well. Okay. So that's kind of the logic, that's kind of the procedure with these types of problems. First, you're going to use the stream functions to solve for the velocity field. Then from the velocity field, you're going to use Bernoulli to solve for the pressure field as well. Okay. This will be kind of our first time in this class. I know we introduced the concept of a velocity field, a pressure field very early in this class, but this will be kind of the first time where we can actually solve for it in practical situations, which is pretty exciting. Okay. Okay. All right. Any questions on that before we start jumping into examples? Yeah, a little bit less than an hour for examples, which is just perfect. Okay, all right, so let's start with our first example, right? So this will be our first time combining stream functions together. Okay, so this is always the first example that's done in potential flow, which is the combination of a source together with a uniform flow. Okay, so let's draw what it looks like at first, and then I'll give you its name. Okay. Okay. All right, so let's go ahead and draw our coordinate axes here. Okay. First, we're going to draw a uniform flow. So uniform flow, at least the way that we've defined it, is going from left to right. Okay. And then our source, right? We know that our source is going to be at the origin, and it's going to be radiating outwards, a purely radial flow. And so our source here has a positive M. Okay. So just like I promised, we can determine a combined stream function for these, where all we have to do is just take the stream function for uniform flow and add that together to the stream function for our source. Okay. Okay, so our stream function here is going to be the combination of our stream function for uniform flow plus our stream function for the source. Okay. All right, so we go ahead and plug in for that. And so our uniform flow, remember, is U times Y. And our stream function for the source is a positive M divided by 2 pi times theta. Okay. That's all it is, right? So we're just adding those stream functions together. Okay. Now it is more convenient to work completely within the same coordinate system. And so you can see here our uniform flow is defined in Cartesian coordinates. Our source stream function here is defined in polar coordinates, so it is useful to kind of have them all in the same system. Okay. So you can go either way. You can go either, you can put the entire thing in Cartesian coordinates or polar coordinates. Usually just because of the way that our sources and vortices and our doublets are defined, it is actually easier to go convert to polar form. Okay. And so basically, if we make the substitution, okay, we know that the substitution to go from polar or Cartesian form to polar form, we plug in y is equal to r sine theta. Okay. Right, so our combined stream function here in polar coordinates is u r sine theta plus m divided by 2 pi times theta. Okay, so that is our combined stream function. It really is just as simple as that. You just take an individual building block stream functions, you add them together. Sometimes you have to convert coordinate systems just so that it's all within the same system, but usually that's not that big a deal. Usually you're converting the uniform flow just because everything else is in polar. Okay. Okay. All right. So let's go ahead and now let's kind of describe what's going to happen. So how are these flows going to interact? And what's the resulting complex flow that comes out? Okay. Okay. So when these two flows interact, right, what's going to happen is that the uniform flow is going to come in, and it's essentially going to be pushed out by the source, right? So the flow from the source is going to come out. It's going to push the uniform flow out. Okay. It's going to come to a head, or I should say, come to a stagnation point at a location there. Okay. So there's going to be some location along the negative x-axis where the uniform flow and the source flow, they're just going to completely cancel each other out. Okay. So this point right here, right? This point right here where the source flow and the uniform flow, they're both they both have the same magnitude, but they're in completely opposite directions, right? So we're going to have zero velocity, right? We already know what those points are called. These are called stagnation points. Okay. Right, so there is going to be a stagnation point in this flow. Most of the time, there is going to be a stagnation point in these potential flows. Okay. And then from that stagnation point, you're going to see a specific contour is going to actually result from this. Okay? And the contour kind of looks like the following. Okay? So essentially, we're going to have a streamline that originates from that stagnation point that kind of forms this really interesting kind of nice contour around the ball. Okay? Where this contour here you can see is the uniform flow and it's being kind of pushed out from the source. Okay. Eventually you're going to get far enough away from the source, like in these locations up here, okay, where the source kind of dies out by that point. And so at those points you still have uniform flow. But close to the origin, close to the source, we have this kind of streamlined bottom. Okay. So this type of combination here, this combination, you have kind of a stagnation point just on one end, and we have kind of a body that kind of extends somewhat infinitely over to the other side. This is what's called a half body. Right, so the basic combination of a source and a uniform flow gives you a half body. Okay, which by itself, I think it looks pretty cool, right? But this half body here kind of forms the basis of a kind of like an aerodynamic streamline type of surface. Okay. Right, so half body is one name for it, but another name that you can call this is kind of flow over a streamlined surface. Okay, and there's a lot of really interesting analysis that we can do on this flow here. Okay, but that's the basics, right? And so when you combine a uniform flow and a source, a stagnation point is going to form, and then a contour is going to go around that. Okay. Now, typically in these types of flows here, we're only really interested in the flow that's going on outside of the body. Okay. So everything on the inside of the body, technically the way that we define our stream function, technically there's flow there, but we kind of just ignore it, right? And so usually our contour from the stagnation point is meant to represent some kind of solid surface within the flow. Okay. So we kind of ignore everything on the inside. Which is good, right? Because what's on the inside of the surface? The inside is the origin. And what do we know about the origin in these types of flows, especially when there's a source or a vortex or a doublet present? The origin is a singularity, right? And so most times we want to ignore the origin. And so by only considering the flow that's going outside of this body, we kind of satisfy that criteria, right? So we're only looking at places where we don't have a singularity, which is generally good. Okay. Okay. All right, so let's go ahead and do some analysis here. Okay, so first thing we're going to do is we're going to look at the stagnation point here. Okay, so the stagnation point is basically the point along the negative x-axis where the uniform flow and the source flow kind of perfectly cancel out. Right? And so we get zero velocity there. Okay, and so we can solve for the distance, right? And so a lot of times we want to find out the distance between that location and the origin. Okay. And so we go back up to our figure here. Let me erase these pink lines here just so that it's a little bit easier for us to see. Okay. Okay. And so essentially what we're interested in is we want to see how far out the stagnation point is from the origin. Okay. So essentially we want to solve for this distance right here. Okay. All right, that horizontal distance from the origin over to that stagnation. So let's call that distance, we'll call it B. Okay. Why we call it B, actually, that's a great question. I guess B is kind of underutilized as a variable in our equations here. Okay. So at that location B, the velocity from our source and the velocity from a uniform flow are equivalent. Okay. And so what we can say is that Vx from the uniform flow is equal to UR from the source. So let's go ahead and use our expressions for our uniform flow velocity and our source, and let's plug in B and let's solve for its value. Okay. Now for the uniform flow is quite simple, right? Remember, so for the uniform flow, right, it's defined in a way where we just have constant velocity all throughout, all in the x direction. Okay. So this is just going to be equal to big U on the left-hand side. And on the right-hand side, we have the velocity for the source, which is m divided by 2 pi times r, but we're going to evaluate r at that location B. Okay. All right, so if we go ahead and solve for B, so this is a pretty simple equation here. Everything else we know, right? So we already know how strong our source is. We know how strong our uniform flow is, right? And we get B is equal to m divided by 2 pi times U. So this right here is the location of our stagnation. Okay, so that's a quantity that we're going to come back to. Let's go ahead and let's go ahead and define other quantities as well. So for this particular case here, this flow around a half body, this has been studied, almost to death, right? It might be one of the very first combinations of potential flow that's out there. And so we have some formulas that are very specific to the half body. Okay. So I'm not going to go through the derivations of these formulas here just because we have more to cover today. But I will kind of just briefly describe how they were formed. Okay. Okay, so the first equation that we're going to solve for here is the equation of the body surface. So basically, this is going to be the equation of the streamline that originates from that stagnation point. Okay. So basically, if you take your stream function, you find the value of the stream function which corresponds to the stagnation point, and then you set that equal to a constant and you solve for the equation of the streamline that results. This is how you get that equation. Okay. So we're going to shortcut all that work and I'm going to give you that equation here. Okay. Okay, so that equation is equal to, we have y is equal to b times pi minus theta. Okay. Right, so that's literally kind of an equation of a line right there. But usually the more convenient form for this is actually to put it completely in polar coordinates. Right. And so we're going to make the same substitution that we did before. So we're going to say y is equal to r sine theta. Okay. So therefore, the body surface equation is r is equal to b I minus theta divided by sine theta. Okay. All right. The other equation that we're going to go over, which is kind of unique to the half body. So these equations, I'm going to box them just because we're going to use them in the next example. But outside of the half body, these equations have no significance. Okay. Okay. So the other equation that we're going to go over, that we're going to use in the next example, is the width of the half body. Okay. Okay. So basically for the width of the half body, eventually you're going to reach a point where the width of that half body is going to asymptote, right? So it's just going to remain constant. Because as you get further and further away from the origin, that source will get, or the effect of that source will get weaker and weaker, okay? And so I kind of drew that up here, right? And so if you look at this half body here, far away from it, the width of this half body here kind of starts to become a constant, okay? So this is the width that I'm talking about here. Okay. And so the width of that half body, we're going to take appropriate limits, and we take the limit of this as it approaches far away. The width is simply just 2 pi times b, where b is the location of our stagnation point that we saw. Okay. And then finally, last thing that we're going to do before we jump into an example here is we're going to look and see how this combines with Bernoulli. Okay. So remember, before we started talking about the half body, we mentioned that potential flow combines very easily, very nicely with Bernoulli, because we're assuming everything here is implicit. So there's no viscosity that's going on. Okay. Okay. So just to kind of remind you, let's go ahead and write out our Bernoulli. And this will be classical Bernoulli, not the modified Bernoulli that we talked about yesterday. Okay. So classical Bernoulli, we have P plus 1/2 rho times velocity squared plus rho gz. Okay. And let's put a 1 on all of these here. Right? This is equal to the same quantities evaluated at a different location within the flow. Okay, so P2 plus 1/2 rho V2 squared plus rho GZ2. Okay. Okay. So in order to plug in for this, we need to essentially plug in for the velocity, right? That's the main thing that we're missing here. Okay. And the way we're going to get velocities is we're going to use our combined stream function. Okay. All right. So remember, we have UR, okay? And we're gonna do everything here in polar coordinates just because our stream functions in polar coordinates. UR is equal to 1 over R, partial psi, partial theta. Okay. right? And so if we take our combined psi, right, our combined string function that we talked about earlier, which is this guy right here, okay? We can take derivatives of this with respect to r and theta, and that's going to give us our velocity components. Okay, so UR in this case is 1 over r partial psi partial theta, right? We plug in our combined psi, we get u cosine theta plus m divided by 2 pi r, okay? And then we have u theta is equal to minus partial psi partial r, which is equal to minus u sine, okay? Because the contribution from the source term does not depend on r, and so when we take the derivative with respect to r, that part just goes away. Okay. Okay. All right, so now that we have the velocity components, we can combine them together to get the speed. Okay. So speed is nothing more than just the magnitude of the velocities. Okay. So speed is equal to square root ur squared plus u theta squared. Okay. Okay. So this is equal to square root. We're just going to take both of these components here and square them, okay, and then add them together. Okay, so I'm going to skip a little bit of the algebra just because I do want to get to D'Alembert's effect and Magnus effect. Okay, and so you plug those in, and what you get is u squared plus u times m times cosine theta divided by pi times r plus m over 2 pi r quantity squared. Okay. So there's a little bit of algebra involved in there, and so part of that is, you know, if you're wondering how we got u squared by itself, remember cosine squared of theta plus sine squared of theta, one of the famous trig identities that equals 1, right? So that was utilized in this as well, and there was some foiling and distribution that we kind of skipped over as well. Okay. Okay, one more simplification that we'll make before we plug into Bernoulli is we're gonna plug in for m here. Right, because m right now is this kind of this nebulous kind of source strength term, which, you know, by itself doesn't have, you know, the most intuitive kind of interpretation. So if we plug in for m, right? Remember we defined m in terms of v, right? So we have this relationship based on the location of the stagnation point, where b is equal to m divided by 2 pi times u, okay? So if we rearrange this equation here, we multiply both sides by 2 pi u, we get m is equal to 2 pi b times u, okay? Okay, and so we do that, we get speed is equal to, okay, speed is equal to square root, right? So that's going to allow us to factor out a u squared. So we have a u squared that comes out here, okay, multiplied by 1 plus b over r cosine theta plus b squared over r squared. Okay, and now this speed, the speed is what we're going to plug into Bernoulli equation. Okay, so that's one thing you have to be careful of when you're using potential flow with Bernoulli, right? So when you use Bernoulli equation, okay, using this formula up here. When you plug in for the velocities, you're not plugging in the components of the velocity itself. And so Bernoulli is assuming that the velocities that you plug in are your velocity magnitudes or the speeds. Okay, so make sure that you compute the speed from individual velocity components before you plug into those. Okay. So in the next example that we'll do, we'll kind of see that in action, but just I wanted to kind of comment on it now before we start putting numbers on this thing. Okay. Okay, any questions on this so far before we jump into an example with the half body? Okay, all right, so let's go ahead and jump into an example. Okay, so one interesting kind of application of a half body is to consider flow that's going past a hill. Okay. And so technically the half body is defined for both positive and negative values for y. So it's above and below the x-axis. But we can consider just flow in one quadrant here, just above. Okay. Okay. And so that looks like the following. So if we kind of draw our image like this, okay, where that hump there represents our hill. Let me go ahead and define a few different locations here. So we'll define location 1 right here. This will be location 3. And then this will be location 2. Location 2 will be right above the origin. Okay, so we're going to assume our origin is at that location here. Okay. All right, so flow is going to come in, right? So we have a uniform flow here. It's going to have a speed of 40 miles per hour. We know the height of the hill, right? So we know the height of the hill far away is going to be 200 feet. Okay. And we know the density as well. So the density of this is going to be 0.00238 slugs per feet cubed. Once again, slugs is just a unit of mass, right? And so this is not actual mollusks. It's just slugs. Okay. All right. And so we want to compute a few different things here. So first, we want to solve and compute the flow at location 2, flow speed. Okay. All right, next thing we want to solve for here is we want to solve for the height or the location of point 2. Okay. And we want to find the pressure difference between location 2 and some point far away from location 2. All right, so this is kind of a practical application of potential flow where, up until this point, potential flow has kind of just been just a lot of just math equations and partial derivatives. So this is kind of an example of how you can actually apply. Okay. All right, any questions on just the setup for this example? Okay, all right, so let's go ahead and get started. So let's go ahead and start with part A. Okay, so for part A, we want to solve for the speed at location 2. Okay, so in that sense, we need the velocity components at location 2. Okay. But in order to plug in for the velocity components, we need the r theta coordinates of that location as well. Right? Because all of our velocity components, all of our speeds, all of our stream functions here, they're defined in terms of r and theta. And so now, we can visually see where location 2 is, but, we need to define, we need to pinpoint it exactly where it is in terms of its r and theta coordinates that we can actually plug that into our equations. Okay. Okay, so to do this, you do kind of need an understanding of polar coordinates in terms of what to kind of plug in. Okay. All right, so let's do theta. Let's do the theta coordinate first, because that one's a bit easier. Okay. So remember, the theta coordinate represents how much you have to rotate from the positive x-axis in order to reach your location. Okay. And so if we start from the positive x-axis here, right? Right, we start with a vector that kind of points horizontally outwards. If we were to rotate that into a position for a vector that points directly at 2, right? That's going to tell us our theta, which is how much we rotate. Okay. And you can tell just from the figure that I drew here that theta here is going to be 90 degrees. We have to rotate counterclockwise 90 degrees from our positive x-axis in order to get to that location there, right? But in order to plug into the equations, we do have to convert this to radians, okay? So 90 degrees in radians is pi over 2. Okay. All right, and so if we plug that in, and so if you go back to our half body equations here, okay, we know that location 2 lies on the body surface, right? And so because of that, we can use this formula here to compute the coordinate of r. Okay. But since location 2 lies on the body surface, we can say that r is equal to e times pi minus theta divided by sine theta. And we know what theta is, and so theta here is pi over 2. We just found that. Okay. And so we plug that in for that. We have pi over 2. This is pi over 2. Okay. We get r is equal to b pi divided by 2. Okay. The sine of pi over 2 is 1, right? So sine of 90 degrees is 1. Okay. All right. And we can actually solve for this as well because, b is something that we can solve for based on the height of the hill, right? So we know we're given in the problem that the hill far away has a height of 200 feet. Okay. If we go back to our equations up here, we can see that the height or the width of the half body is 2 pi times b. Okay. All right. And so if we use that information, we say the width is 2 pi times b. Okay. So the 200 feet, or the height that we're given in the problem, is actually half the width. And so what we can say then is 200 feet is equal to pi times b. We just essentially just divide it by 2. Okay. And so what we get is b is equal to 200 divided by pi. Okay, good. All right, and so if we plug in for that, then we can say that r is thus equal to 200 divided by pi times pi over 2. And so that's 200 divided by 2, which is just 100. Okay. Okay, so knowing r knowing B, knowing theta, right? Right, we have everything we need to plug into our speed equation, okay? So I know this is a little bit rapid fire, but I do want to get to flow over a cylinder because that is kind of really important, okay? And so we have everything we need to plug into our speed equation here. Okay, so we kind of did this example kind of in a little bit reverse order, where we derived all the equations first, and this example here is just kind of applying those equations from there. Okay, but if we plug in for speed here, we know what u is, we know what b, we know what r is, we know what theta is. Okay, we plug in for all those, we get speed is equal to 47.4 miles per hour. Okay, good. All right, and so one thing I'll note here, before we move on to part B, one thing I'll note here is that, notice that the speed going around the hill at point B, this is actually greater than our uniform speed of 40 miles per hour, right? So remember in our problem, we have U is equal to 40 miles per hour, right? Okay. And so standing on that hill, we actually experience a higher speed than the uniform wind speed that comes around. Okay. And the reason for this is that, the flow has to basically accelerate to get around the hill to maintain conservation of mass. Okay. Okay. All right. Good. So that's part A. Okay. Let's do part B. Okay. So part B of this problem asks us to solve for the pressure difference between a point that's far away and the pressure at location 2. Okay, so essentially we're asking to solve for the pressure at location 2. Okay, and so in order to do this, we do need our Bernoulli equation. Okay. And luckily, some of the work we just completed already, right? So we already know what the speed is at location 2, right? All we have to do is just pick another point in the flow that's far enough away and then use Bernoulli from there. Okay. Okay, so if we set up Bernoulli here, we have P1 plus 1/2 rho V1 squared plus rho GZ1 is equal to P2 plus 1/2 rho V2 squared plus rho GZ2. Okay. Where everything on the right-hand side of this equation, this is going to be evaluated at location 2. Right? And then the speed that we just solved for, the 47.4 miles per hour, we just plug that right into the kinetic energy term for that there. Okay. Now for the other side, we're going to pick a point that's far away, but we're going to pick a point that's far enough away such that we're going to be far enough away from the source such that this would be evaluated at just the uniform flow. And so at the uniform flow conditions, we are not really affected by the source, right? And so we go back up to our figure here, right? So let's say for our Bernoulli equation, we're going to pick a location kind of right here, okay? So we'll call this location B for Bernoulli, okay? So at location B, we haven't even hit the hill yet. And so the only flow that we're experiencing, the only velocity that we're experiencing is that 40 miles per hour from the uniform flow, okay? All right, and we're essentially going to take a path right up to the hill. Okay, and so for that sense, then this u here is going to be this v is going to be 40 miles per hour squared. Okay. And if you notice the way I drew that, we're using the same trick that we always do with Bernoulli. We pick 2 points with the same height, right? And so in that case, we can cancel out the 2 z coordinates here as well, okay, the potential energies. And so what we can get from that is P1 minus P2, right? We kind of plug in and we evaluate everything. We get 9.31 pounds per feet. Okay. Any questions on that? Yes.
Are all these problems gonna be in radians? Will there be no degrees?
Yeah, so for the most part, if you're plugging into an equation that has just theta, you have to assume that's radians. Yeah. Okay. All right. So don't have too much time for this. Maybe we'll go over this a bit on Tuesday. Because this next part I think is the coolest part. So we kind of did all the hard work, so now we can actually see some cool stuff. Okay. So last thing I want to go over today is flow around a cylinder. Which I know doesn't sound exciting, but there's actually a lot of really interesting phenomenon and a lot of really interesting applications for this as well. Okay. All right, so flow around a cylinder is exactly like it's described, right? So we have a cylinder here. We're kind of looking at it kind of down the barrel. We have flow that's going around the cylinder to something. Okay. Okay, so to get flow around a cylinder, we are going to combine a uniform flow together with a doublet. And so we add those two together, and then also making the conversion to polar coordinates. We get psi is equal to UR sine theta. Okay. So that's our uniform flow in the polar coordinates minus K sine theta divided by R. Okay. All right, so same thing with the half body. We just take our basic string functions and we just add them together, and then that gives us our combined flow. Okay. Now, same thing with the half body. We're going to take a geometric quantity of this flow and then kind of recast our stream function in terms of that, just to make things a bit more clear. Okay, because this doublet strength K, right? It has a mathematical meaning, but physically, it's not the most intuitive thing in the world. Okay, so what we're going to do is we're going to say that our cylinder is going to have a radius A, okay? And we're going to recast our stream function in terms of that radius A, okay? And so in order to do that, our doublet strength K here has to equal to U times A squared. And so with that, we get a little bit of a cleaner form for the stream function, okay? And so we make that substitution, we get psi is equal to U times R times 1 minus a squared over r squared times sine theta. Okay. So that's our stream function. And we can go through the exact same exercise that we did before, right? So we can take the stream function, we can take its derivative to get the velocities. From the velocities, we can find its speed, and then from the speed, we can plug into Bernoulli to find pressure. Okay. Okay. So those are all the steps. Unfortunately, we don't have time to go through those steps, but it's kind of the same kind of song and dance we did for the half body. And so it's just kind of the same process that we did there. It's just the equation's different here. Okay. But eventually, you do all that, you can find an expression, or we can find an equation for the pressure field within this flow around a cylinder. Okay. And the pressure field is actually very interesting here. Okay. And so we do that, we get the following. And so pressure at some location downstream of the cylinder. And so we basically followed a streamline from the upstream of the cylinder down to the downstream. This is equal to P naught plus 1/2 rho u squared times 1 minus 4 sine squared theta. Okay. Right, so that is the theoretical pressure distribution around the cylinder. Okay. Okay. Now, this result is actually very, very interesting. Okay. Because if we plot this out, right? So we plot this out over different values of theta, right? Where you can imagine that we plot this from theta is equal to pi over 2 down to theta is equal to 2 pi, right? That's going to give us an expression of how pressure varies from the front of the cylinder to the back of the cylinder. Okay? And so if we plot this, right, where the horizontal axis here is theta, where here on this end is going to be the front end of the cylinder. This other end is going to be the back of the cylinder. Okay. We end up with the following kind of profile. So we end up with kind of a symmetric profile. So the pressure, starts out high at the front of the cylinder. As you go around the cylinder, the pressure does drop, but then by the time you reach back up to the back end, the pressure actually recovers. Okay. Right. And so kind of the upshot to this is that the pressure on the front and the back of the cylinder is the same. Now, why is that significant? Why is that such an interesting result? Okay. So what do we know about pressure, right? So think back to our unit on hydrostatics, from the very beginning, right? If you have a pressure, a fluid pressure that's going to be exerted on a surface, that essentially is a force, right? So pressure exerts a force on a surface, okay? If you think back to the potato chip problem on the last midterm, right? So on the last midterm, I asked you guys, what happens when you bring a bag of potato chips to the mountains, okay? With the hint that I told you that potato chip was bagged at sea level, okay? Now you go into the mountains, and most of you kind of caught this, that you go to the mountains, you experience less atmospheric pressure there, right? Just because you're at a much higher elevation. And so what happens then is that inside your bag, you have a sealed bag of potato chips. You have atmospheric pressure inside. On the outside, you have much less atmospheric pressure. So you have kind of an imbalance of forces. So you have more pressure on the inside than you do on the outside. What's going to happen is that the bag is going to inflate, right? And so most people kind of got that from the exam. Okay. And so because of that imbalance in pressure, you have kind of a net force that kind of pushes the bag outwards. Okay. We don't have that here. And so what we have here is that our pressure is the same in front and the back. Okay. And so that tells us that there's no net force that's going to be on the cylinder sitting in this flow. Okay. In other words, there is no drag force on a cylinder that's sitting in a uniform flow field. Now we haven't talked about drag force just yet, but you can kind of infer here that drag force is kind of a force that's that kind of arises from fluid mechanics. Okay. Okay, so basically, and if you kind of generalize, so you can think of, the cylinder as a person, right? So so what this is telling you is that if you have a uniform flow field, right, you can think of any uniform flow field. You can think of like a river, right? And a human body is roughly a cylinder, right? So if you kind of stand with your arms to the side, you're roughly cylindrically shaped, right? And so what this is telling us that if we stand in the river, right, as a cylinder, we are not going to be moved along with the flow. So the flow is just going to go around us, and we're just going to be like Jesus in the flow, and the flow is just going to go around us, and we're just going to feel no force, right? Obviously, that's not true, right? And so this is a situation where kind of what we experience in reality is different than what the theory predicts, okay? And this one in particular is a very famous one. So this one's called D'Alembert's paradox. Right? It's one of the very kind of famous paradoxes in fluid mechanics. Okay, so what potential flow doesn't account for, and we've kind of said it over and over today, is that potential flow does not account for any viscous effects. Okay, now viscous effects affect flow around a cylinder in a very interesting way. Okay, and so if you have flow around a cylinder like this, right? What tends to happen in reality is that because of viscosity, you have what's called flow separation. Okay, so the flow is going to come in, it's going to hit your cylinder, right? And instead of hugging the cylinder all the way around, there's going to be a point where the boundary layer kind of separates from the cylinder, okay? And then a wake region forms. Okay, so you basically have kind of chaotic kind of vortexy flow around in the back end of the cylinder because you have viscous effects and boundary layer separation. Okay, and so because of that wake region is kind of what creates the drag force. Okay, now we'll talk more about drag force kind of later on in the semester. Probably in the last week, probably on Tuesday of the last week. But this is a situation where the potential flow, the theory kind of breaks down in terms of what we experience in reality. Okay, because of that very important assumption of inviscid flow. Okay, all right. Any final questions on this? Okay, so I didn't get to finish everything, so we'll talk about baseballs and golf balls on Tuesday because I think that's also very interesting as well. And so basically what we're going to talk about on Tuesday is that if you were to add some spin to this, and so if you add to a vortex, you can actually create some lift and drag forces just very naturally. And those are actually predicted very well by potential flow. Okay, so we'll start with that, and then we'll move on to our next topic in the class, which is dimensional analysis. Okay. All right, so thank you guys for coming today. Remember, homework 3 is due on Sunday. If you have questions on it, don't be afraid to email me. I should be available all day tomorrow. But if not, hope you guys have a good weekend, and I will see you guys on Tuesday.
Professor, quick question. Um, I'm kind of a little bit confused on where we left off. The subjects that are going to be the concepts that are going to be covered in midterm 2. Did we start in week 2 fluid kinematics? Is that
Yeah.
where?
So basically, the last thing that was covered on midterm 1 was Bernoulli equation. And so everything after Bernoulli equation up until our lecture yesterday, that's going to be on midterm 2. So if you look at the study guide that's on, if you go to the Canvas site, week 3, part 3, the study
Okay.
covers everything you need for the exam.
Okay. Okay. Got it. All right. Thank you.
Yeah.